is that we're left with this notion of, one of these days I'll fall off the thing and file a juicy workers' comp claim.
I hope nothing falls into the built in front of you.
I know, that would be bad, right? Okay, so here's this object. Here's the deal. If I exert this thing, this is 1 kilogram, has a mass of a kilogram. It weighs 9.81 newtons roughly on the surface of the Earth, roughly on the scale, but exactly, more or less, right? Okay, now if I don't accelerate this thing, if I move at a constant speed up and down, I'm not accelerating, it reads roughly 9.81 newtons, doesn't it? You can see it's reading a little bit less when I stop and turn around, yes? Okay, if I do the Willy Wonka thing, move the elevator sideways, yeah? Okay, it reads 9.81, yeah? You guys are like hypnotized. There we go, right? Okay, but if I ever accelerate down, it reads less. Do we see this? Watch, accelerating down. Do you see it read less? And you feel less? And if I ever accelerate up, it reads more. Yeah? Now there's 2 ways to accelerate up. One way is to start at rest and move upward. The other way is to stop going down. Do you see that? Right, if I stop going down, watch when I stop. Boom, big reading, yes? So that's the climber falling on the rope. That's the elevator stopping going down, right? And there's 2 ways to read less than the weight. One is to start going down, and the other is to stop going up, right? It's like, whew, there we go, right? Okay, so, and now the dismount. Okay. In general, stop. Okay. In general, when we're solving these things, here's the deal, okay, is that in these problems, it's always this way. It's always some unknown force minus the weight equals m times a, right? This is sort of like the general form of it, right? I'm giving you some ways to cheat here, okay? So can't I write it this way, that the force is equal to mg plus ma? Can't I write it that way? So the force in general, the tension in an elevator cable, the tension in that rope, is equal to the weight if I'm not accelerating it. And if I'm accelerating up, it's more than the weight by ma. Does that make sense? You need not only enough force to hold it against gravity, but you need enough force to accelerate it against gravity, right? So that's why it's plus ma. And then of course if the acceleration is negative, it's actually less than the weight, because ma would now be a negative term, wouldn't it? That's kind of slick, isn't it? In fact, we could even write it this way, that it's m times g plus a, right? So all of these things can be done that way, right? And then the other trick we'll just go back to the problem that we started with, okay? The problem we started with was that we had 5 kilograms and we had 35 newtons of force. And I said the answer is not 7, but I really lied a little bit, okay? Because the answer we arrived at was negative 2.81. Do you remember that? It'd be amazing if you did, but the answer is that it actually accelerates down because 35 is less than 49.05. Do you remember? Is it all coming back to you? Okay, so the answer was negative 2.81. Now what's the difference between negative 2.81, the answer we got, and the 7 that we thought it was without gravity? What is the difference between positive 7 and negative 2.81? Negative 9.81, yes, isn't that right? Okay, that will always be true. So anytime you want to, you can just totally cheat. Whenever it's a mass hanging on a string, now anything else you got to be careful, but mass hanging on a string problem, you can always just go F over m minus g, right? You know, because it's always going to be like that. It's always going to do that. And the reason for this, it's actually based in, all of these things are basically, this is a principle of general relativity. Okay, here I'm saying that this mass here, this is an inertial mass, this is a gravitational mass. We're saying that they're the same thing, essentially, right? And so here I'm saying that the force needed to hold you up is a combination of the Earth's gravity and the acceleration of your reference frame. This is a weird thing, but let's just touch on it. One of the tenets of, it's called the principle of equivalence, the equivalence principle, okay, states this, that there's no difference between this feeling that you have of like there is gravity and if we put you in a little box in space and accelerated you that way at 9.81 meters per second squared. There's no experiment you could do in physics that would determine the difference between that. Isn't that weird? That's sort of weird, isn't it? One obvious experiment would be you could go outside and look and see whether you actually are flying through space in a small box. But besides that, right, there'd be all the laws of physics would work the same. When I drop the pen would stop accelerating that way and would accelerate toward the ground would accelerate into it, yes? If we were in that box in space accelerating at 9.81 meters per second squared. So that's why this works, is that if we are accelerating the object up, we've actually just put it in a frame of reference where there's more gravity. Or if we accelerate it down, it's in a frame of reference where there's less. And this is not just voodoo. Are you okay? This is not voodoo. This is actually based on relativity, which is very cool. And now I need to tell a totally unrelated story